Hi everyone, my name is Phong and this is my teammate
Nishan.
I'm Rohit.
I'm Hari.
So in the presentation today, we will present our work on our Beamsonic chip. So first, I will go over the beamforming chip, the concept and the architecture. So as you all know, the ultrasonic sensor is often used to in robotics and radar applications where the range of the object is often the object is the parameter of interest that we want to measure. In such system, in order to create a beamforming and in order to steer the beam, the sensor is often being mounted on a servo, and then we mechanically steer the servo in order to steer the beam. However, that approach is requires a lot of mechanical mechanism and is prone to failure and high maintenance cost. Therefore, in here we decided to have an approach where we borrow the concept of beamforming in millimeter wave down to ultrasonic frequencies. So in here we have 4 transmitter and 1 receiver, and this one showing the beamforming in MATLAB, and you can see that there's um, a a main beam, and also there's a side beam that is very large compared to the main beam. And this problem can be fixed if we use like a smaller footprint sensor. So for this version of the PCB, we use an MA40S4S that has a pitch of 1.2 lambda or 1 centimeter, but there's a footprint out there that has smaller pitch. This one is the architecture of our system. The main chip has transmitter and the receiver. So in order to understand how it works, we can start with the FPGA. So the FPGA is used to send 5.12 megahertz clock to the chip, and then it has 2 frequency divider blocks in order to generate 2.5 megahertz and 40 kilohertz. And these 2 clocks are used to generate the phase shifter and the 40 kilohertz signal at the output. And then we have off-chip power amplifier that is used to magnify the signal and then to drive the transmitter transducer. And so the signal go out and it bounces to the object, come back to the receiver sensor, and then on the receiver system we have an LNA, bandpass filter, variable gain amplifier, mixers, and comparators. And then basically when we see the signal coming back, we should be able to detect the object from the comparators. And that comparator output is fed into the counters, and then we use the counter to detect the distance between the board and the object. And this is our target. Target. We want to have a maximum range of around 10 meter a system, a range resolution of 2 to 3 centimeter, angle resolution is less than 1 degree, and the maximum range of angle is less than 30 degrees. So I will go over the transmitter, the design of the transmitter system. As you can see, the transmitter system, as I mentioned earlier, it has a frequency divider block that is used to generate the 40 kilohertz and 2.56 megahertz. It also has a sequence generator block that is used to generate 8 or any specific number of pulses that we want. It has a phase generator that is used to generate the phase. And then envelope extender. That block is used to generate the signal, the switching signal that is going to the LNA. Basically, we want to turn off the LNA when the transmitter is transmitting the signal, and then turn it on again to detect the signal. And by doing so, we can avoid the direct coupling between transmitter and receiver. In the transmitter system, we also have an SPI block, and this block is used to program the switch configuration on chip. It also used to program the number of pulses in the sequence generator, and then the phase for the phase generator block. This one is a simulation results of the phase generator block. Basically, the phase generator is a block that is used to generate 60 different phases, and then in here showing from phase 1, phase 10, phase 20, 30, 40, and 60. And then depending on the mux that can use to select whatever phase we want, we can generate the specific phase at the output. And in here we are able to achieve a minimum phase delay of less than 10 degree or 5.625 degrees specifically, and then the maximum phase delay between elements from element 1 to element 60 is 332 degree. This one is showing the simulation results of the whole receiver system, whole transmitter system. So we will start with a trigger signal from the FPGA, and then when the chip receives the trigger signal, it generating pulses. In here, we program the pulses to be 4 pulses, and all the output have the same 0 degree phase. They're all at 40 kilohertz. After the transmitter complete the pulse generation process, it generates trigger signal to start the counter, and then finally it sends another switch signal to the LNA to turn on the LNA. Now I will pass to my teammate Rohit to talk about the receiver system.
I'll explain in detail how the receiver system is able to detect the distance now. Two parameters that are very useful in detecting the distance for our receiver system. One is the noise level that we are able to target, the input referred noise level basically of our RX system, and the second one is basically to increase the distance measured from the transmitter to receiver. We need to make sure that we have a very wide range, a very wide dynamic range without the output oscillating. So these are the most important challenges, I would say, in the receiver system. So let's see how we tackle those issues. So this is our basic architecture, basic top-level view of the RX. We have an LNA which has a gain of 28 dB. We have 2 stages of PGA, each configurable up to 40 dB. So we can have from 0 dB to up to 80 dB about. So the total dynamic range, total gain of the chain can go from 28 dB to about 120 dB. Sorry, about to 110 dB. Then we have the self mixer, which is used to based on the level of the mixer, we can either detect the mixer and the comparator gives either a 1 or a 0 when we have an object to detect the object. Based on the challenges that I mentioned, we need to make sure that at the maximum gain setting, we need to ensure that there is no oscillation. So the layout of the chip has the layout considerations of the chip has to be clear. And second, to make sure that we are able to detect a very wide range at the maximum gain setting, we need to make sure that the input referred noise level of the system is low, which means that at 40 kilohertz and lower frequencies, we need to ensure that the flicker noise at the input is low, and also that the total integrated total noise has to be lower. So how did we tackle those issues? So we'll go into that detail in a minute. So the first stage is basically the LNA. So we see that the unloaded gain of the LNA is about 28 dB, and the input referred noise with the sensor is up to 5 nanovolts per root hertz. So this meant that the sizes of the devices are very large to make sure that the flicker noise is not coming into picture. And most importantly, we have to go for a very high bias in this case. So the biases are set up by using an external resistor in the PCB at the PCB level, and then varying the resistor to control the current that is flowing into the gate. So that current is then used to bias the entire circuit. So this is just a normal resistive loaded, passive loaded differential. It's a passive loaded differential OTA, which is used to generate a differential signal. So this signal, the LNA out plus and LNA out minus, are then used to drive the PGA, which is the next stage. So the next stage is the PGA 1 and 2 are basically one is basically set up as LPF and the other one is HPF. Why? This is very important to reduce the total integrated noise because we only care about the signal at 40 kilohertz. So this means that we can reduce the noise at the coming from the other frequencies by just using a bandpass filter at 40 kilohertz. So this having a HPF and an LPF configuration, the PGA, helps to reduce the total input referred noise. And we can also configure the gain of the HPF by just varying the capacitors at the input and the output. So we have a set at the inverting arm of the op amp and also at the feedback arm of the op amp. So the ratio of these two will determine the gain setting basically. So that is how we determine the gain. We change the gain from 0 dB to 40 dB in this stage. And similarly in LPF, the LPF is just a normal LPF. So we can just change the gain by just varying the ratio of the resistors in the feedback arm and the inverting arm. So that is basically how we change the gain. Let's see how exactly the gain varies. So as we change the gain control settings from 0, 0 to 1, 1, we see that the gain changes from about 0 dB to up to 40 dB in each of these stages. So we get up to 80 dB 80 dB gain variation by just varying the control bits in the PGA. Now the next stage is one of the most important stage for our for detecting the signal. So we have a self mixer which is used to detect the DC level at the output. So basically, if we have an object and if we want to detect the object, so we just use it is just a normal Gilbert mixer. So we have a differential signal coming in from the PGA, and this is used to drive the differential Gilbert mixer here. And the bias here is also controlled by using an external resistor in the PCB level. So the output of this mixer has to drive the comparator. So the common mode of the mixer output is set so as to ensure that the comparator works. The next stage is basically where we have a hysteresis to detect the glitch, and also we need to ensure that when the mixer level is is varying beyond a particular limit, we need to ensure that we need to decide if that object is being actually determined. So to do that, we have a hysteresis, a static latch based comparator. So the current is also controlled by an external resistor here, and then this used to and the differential output from the mixer is used to drive the comparator here. The static latch then decides if the output is beyond the threshold, it's just gives a 1 and is beyond, it says compares to 0. This output is used to drive the next stage, which is basically the counter, but it also has to drive the level shifter because in that case, so we need a driver. So that's why we have an inverter in this case. The switching threshold is just controlled externally by using a VREF here. The counter logic, we have two counters. So when we decided to make the system, we had an issue with the glitches, especially because we get an 8-bit pulse, 8 pulse from the 8 pulse from the transmitter. We need to ensure that if we detect any signal which is less than 8 pulse, it means that either we are missing 2 pulses or something like that. It means that it could be a glitch. So in that case, we need to ensure that the system doesn't detect an object in that case. So how do we do that? We have a 5-bit counter to check if the comparator output is actually 8 pulses. And if the comparator output doesn't reach 8 pulses, then the counter doesn't proceed to count. the 12-bit counter is actually the one that is actually counting the distance between the transmitter and the receiver. So as soon as we saw that from Fong's picture earlier, we get a signal, a trigger signal for as soon as the object is detected, and the counter starts counting the delay then. Now, only if the 5-bit counter tells that the comparator output is 8-bit, it will proceed. Otherwise, it will drop the data because we detect it as a glitch. So the 12-bit counter will count the delay between the transmit and the receive pulse, and it will then send this data to the FPGA, which will then display this data on the LED. So this will be clear when you see the demo, which will be later. Now I'll pass on to Fong to explain the top-level simulations.
So in order to fully test the chip along with the PCB that is associated with the chip, we create a test bench that includes the Beamsonic chip at the center, and then we have an off-chip power amplifiers block in here along with the transmitter sensors, and then we have a path loss model that model the delay and the attenuation of the environment along with like the receiver sensor in here. And then the chip also with the off-chip capacitor is the main thing that is well, we want to test, and it has all like the bonding wire, ESD, and packaging effect that we want to also include in the system test bench. In here, there's a varied biasing block for the receiver and for the VDD supply, and then we have like various voltage sources in order to emulate the effect of the FPGA. This one is top level simulation results. Again, as you can see in the previous simulation results, we have like a transmitter, we have an FPGA trigger from the FPGA that is sent to the chip, and then we have 4 output signal at the transmitter. In this case, they have like all the same phase at 0 degree, and they have 8 pulses. And then after that is the trigger signal that is used to start the counter, and then a switch signal that is used to turn on the LNA. And then when the signal going out and then bounce to the object going back to the receiver. So in here we have the receiver input, and then LNA output plus and minus, and also PGA, and then finally we have the mixer output that is showing as an envelope of the PGA output, and then the comparator. Now I will go ahead and after like the simulation is done, we will move on to the PCB design and the measurement when we have a chip. So this one is the die of the chip that has both the transmitter and receiver, and the chip dimension is 1 millimeter by 1 millimeter, and in here we have like the PCB design for the to test the chip. It basically has some chip socket at the center and surrounded by a bypass capacitor. It has a one section on the top left which is used for LDO circuit, and then on the top right is various resistor and potentiometer for biasing the receiver. On the bottom left we have the level shifter that is used to convert from 3.3 volts to 2.5 volts and vice versa, and that is used to interface between the FPGA and the chip. On the bottom right we have like the power amplifier circuit, and then we have 4 transmitter and 1 receiver. This one is our measurement test setup, where we have the that you will see later where we showed in a demonstration. But basically we have like the whole system that is sitting on the table, and then we have a ruler that is measuring the distance between the table and an elevated object. In here we are measuring from 0 centimeter up to 160 centimeter, and by varying the object height, we can record different distance between the PCB and the objects. And this one is a picture of the test setup along with like the waveform. And this is a detailed picture of the waveforms where we have like the FPGA trigger signal, the 8 pulses from the transmitter, the receiver signal, specifically the PGA output, and then the comparator. So we implemented multiple measurements from 20 centimeter up to 160 centimeter, and on the x-axis is the actual measurements that is measured by the tape between the object and the PCB, and on the y-axis is the measure distance on the both oscilloscope. And well, you can see that the measurement data follow a linear line with a regression coefficient of 0.998004. We also want to demonstrate the beamforming effect by trying to steer the beam from 0 degree to 15 degree. As you can see, like that's showing a difference of, from 160 centimeter to 165.8 centimeter. However, this distance is barely measurable in the oscilloscope, and therefore we haven't been able to demonstrate the beamforming effect. But this can be they can be shown if we can move the setting to like an outdoor environment where the object when the distance between the PCB and the object is further away.
Hi everyone, this is our Beamformer test bench. We have an FPGA to generate control signals for SPI and also read from the counter and then display onto the counter by converting the signal from PC to decimal and then displaying onto a 7-signal LED. Now this is our board. Here we have one section that is for actually driving the 4 different transmitters, and then one section is for the receiver, and this is the socket for our chip. And we have an extra setup for controlling the gain of the PGA. On the oscilloscope, you are actually seeing the trigger signal, then actually our 8 different pulses for the transmitter. Then this one is actually the output of our PGA, and then finally the comparator output. And as you can see, if I move my hand closer, the comparator output is in time domain is getting closer to the transmitted pulse. If I move it further apart, the comparator output is going further away. So is it with the comparator, with the counter. The counter is calibrated for a wave velocity of 340 meters per second. And as I move my hand closer, you see that the counter value is approximately giving the vertical distance between my palm and the board. And if I move it further, you see the distance also go up. And so is it a demo with different objects, including a large plate and an iPad.
You'll see a quick demo with different size, different objects. So we see that with only the hand, we see a single pulse, which is expected, and the counter gives the distance in millimeters. As we go closer to the receiver, we see that the distance shown by the comparator is changing proportionally. Now we'll do the same thing with 2 different objects. We'll see a medium-sized object here. It shows that there is a wider pulse because there is multipath here, multiple deflection from the board itself and also from the transmitter. We see that this is also moving as the object is moving farther away from the transmitter. Right now, with the current PGA configuration, we can detect up to closer to 900 millimeter. Beyond 900 millimeter, there's destructive difference. Similarly, with the even larger size object, we'd expect, because of the multipath, we can even expect to reach similar things. But as we move closer to the transmitter, we see that there are like multiple reflections from the PCB board itself, which is as expected. That's it for the demo. Thank you for joining us.
Finally, We would like to thank Professor Peter Kinget for his guidance and motivation throughout the project. We would like to thank our TAs, Armand, Alfred, and Jose for spending many nights helping us debugging the chip. And we also like to thank our other teams in the course that are helping us with like brainstorming the ideas and learning, and also many discussion throughout the year. We also would like to thank Columbia University and Apple for providing us the opportunity to build a complicated chip for the tape out, and we glad that we made some mistake and we were able to correct it before the tape out, and then that would equip us many valuable experience for like future complicated system. And finally, we would like to thank our team classmates and friends for many insightful discussion and memorable experiences.